A hypothetical planet of mass m has 3 moons, each of mass m, each revolving in the same circular orbit of the radius r. The masses are equally spaced and thus form an equilateral triangle. Find the potential energy of the system. Now, first of all, we will find out the potential energy, and the second thing we have to find out is the orbital speed. In order to find out the potential energy of the system, let us find out how many masses are there. Okay, there are basically 4 masses, the planet having a mass m, and there are 3 satellites each having mass small m. Okay, and its distance from the planet is equal to r. So basically, the potential energy of the system will be first between a planet and the satellite. Okay, so if I consider this planet and the satellite, let me consider this potential energy between one planet and one satellite. It will be equal to small m capital M divided by r. Okay, now this is the interaction energy between one planet and one satellite. So the interaction between a planet and 3 satellites will be simply multiplied by 3. So the total potential energy between the planet and the satellite, it will be equal to, for a planet satellite configuration, it will be equal to 3 times gm divided by r. Okay, it will be equal to 3 times gm divided by r. Let this be equation number 1. Now this is the total potential energy due to the interaction between the planet and the satellites. Now let me consider the interaction energy between 2 satellites. Okay, now let us first find out this distance. We can find out this distance by using the equilateral triangle, the altitude for the equilateral triangle. If I say this distance is equal to r, this distance, the altitude will be over here equal to, root 3 divided by 2 into small r, and the distance till the centroid, the planet will be situated at the centroid, is 2 by 3 times root 3 by 2 into r, that is root 3 by 2 into altitude. So basically 2 and 2 will get cancelled out, root 3 and this will become root 3. So I can say that capital R over here is equal to r divided by root 3, or r will be equal to root 3r. Okay, so the potential energy between a planet and 2 satellites, it will be equal to g m1 m2. So it will be equal to m square divided by over here it will be equal to root 3r. Now there are 3 such configurations between first and the second satellite, between first and the third, and between second and the third. So this will also be multiplied by 3. So the potential energy between the between the satellite configuration, it will be equal to 3 times. So it will be equal to root 3 gm. So it will be equal to root 3 gm square divided by r. Now let this be the second equation. So the total potential energy of the system will be equal to the addition of the first and the second. So I can take 3 common, okay, and I can also take gm by r common. It will be equal to mass capital M plus small m divided by root 3. Okay, it will be equal to small m divided by root 3 when I add and I take gm by r common. Okay, 3 gm by r common. Okay, now I got the potential energy of the system. Okay, the second thing I want to find out, the first part is done. Okay, so the second thing I want to find out is the orbital speed of each moon such that they maintain their configuration. Okay, now it is not specified whether the mass of the moon is very small as compared to the mass of the planet. So I cannot ignore the mass of the moons, okay, or the satellite, okay, as compared to that of the planet. So I have to take all the masses in consideration. Let this distance be equal to r. Okay, this distance is equal to small r. We will substitute the value of small r later. Okay, now over here there are, how many forces are acting on this satellite? Let me consider the satellite A. So how many forces are acting? The first force is acting between the interaction between the first and the second satellite, between first and the third, and the interaction between the satellite and the planet. Okay, now if it forms an equilateral triangle and this is an altitude, this angle over here will be equal to 30 degree. We will use this angle later. So let me first find out the force between the 2 satellites. It will be equal to g into m square divided by r square. R over here, okay, let me substitute it as r square initially. Okay, so this is the force acting in the left, in this direction, okay, between the first and the second satellite, and this is the force acting between the first and the third satellite. Okay, now if you see in this direction, that is in the sine component, it gets cancelled out, and in the cos component it will get added. Okay, so basically the total force that is acting towards the, let us say, center O will be equal to, due to only the satellites, it will be equal to gm square divided by r square. Now r can be substituted as r into root 3. Okay, so it will be equal to root 3 r the whole square into cos theta. Okay, into cos theta. Okay, only the cos component will be added, the sin component will get cancelled out. So basically the force due to one satellite in the direction of O, it will be equal to gm square divided by 3r square cos 30. Cos 30 is equal to root 3 divided by 2. Okay, cos 30 over here will be equal to root 3 divided by 2. Now there are two such satellites between first and second and between first and third. So the total configuration will be multiplied by 2. So basically it will come out to be gm square. When I multiply this equation by 2, it will be equal to 2 and 2 will get cancelled out. Gm square divided by r square into it will be equal to root 3. Okay, let this be equation number 3. Okay, let this be equation number 3. Now this is the force only between the first and the second and the first and the third satellite. There is also one force acting between the satellite and the planet situated at the center. That force will be equal to, that force over here will be equal to g small m capital M divided by r square. Okay, so the total force over here will be equal to, so the total force acting will be equal to g m by r square can be taken as common. It will be equal to m by root 3. Okay, it can be taken as m by root 3 plus capital M. Okay, plus capital M. Now this force over here will be equal to the centripetal force, which is equal to mv square divided by r. Okay, it is equal to gm divided by r square into m by root 3 plus m. So which is equal to mm will get cancelled out, it r and r will get cancelled out over here. So over here v can be equal to root of g by r into small m by root 3 plus m. Okay, so this is the total velocity of the satellite. Okay, velocity that all the satellites must maintain in order to maintain their given configuration.